Yeah, so there we go. So, hello, everyone. I know that it's been a full day. I'm tired, you're tired, so I promise I will make this next 30 minutes both interesting, but most importantly, also fun. So, who am I? My name is Nico. I'm a freelance front-end developer from Switzerland. I'm also part of the Google Developer Experts program for web technologies, which basically means that I spend way too much of my free time just playing around with all kinds of new web APIs, browser APIs, everything that is exciting in the web. And I also like to talk about those subjects. So in the last couple of years, I had a couple of talks, almost all of them in English, some in German, but only 2 talks in Berndeutsch, which is my local Swiss German dialect. And in September 2021, I had my very first talk in Berndeutsch, and it was recorded, so I'm able to give you a short clip of that talk. Let's hope the audio works. Oh, wait, it does not. There we go. Im Endeffekt und schlussendlich, im Endeffekt ist im Endeffekt, schlussendlich, das im Endeffekt, wird im Endeffekt nur im Endeffekt, aber im Endeffekt, schlussendlich, im Endeffekt, schlussendlich, I think you see where this is going. So that was a 30-minute talk, and I managed to use the words im Endeffekt and schlussendlich over 35 times. And that was so annoying to me when I saw that video afterwards. So a couple of months ago, my second talk in Swiss German was right around the corner, and I was looking for ways to detect those words when I'm speaking. There are browser APIs like the speech-to-text API that works incredibly well in English and also in German, but certainly not in Swiss German. But then again, those APIs, they are basically just using machine learning models, right? And can't we use them directly in the browser? Turns out we can. So I would like to give you a short introduction into what machine learning is and how we can use machine learning in our applications. But let's start with some basics. Let's imagine we have a little toy car, and we want to add some self-driving capabilities. So we will add a sensor. Whenever the sensor reaches a certain threshold, it will turn 180 degrees. Yes, we have our self-driving car. But it's not very smart. Let's add more sensors. With 2 sensors, we can now predict whether it should turn left or right. Code gets a little bit more complex, but I think we're fine. That's still maintainable. But let's add more sensors, because we want to be able to detect objects in front of us. So now we have 6 sensors in front of us. We are able to detect those objects, but our code gets really messy super fast. And imagine those are just the sensors in the front. Imagine we have road signals, imagine we have other cars, imagine we have weather. All that data feeds into our algorithm, so there's just no way we can maintain an algorithm in a classical way. We need something new. We need a magic prediction black box, where we can just feed in all the data, and it will figure out whether we need to turn, whether we need to adjust the speed, whether we need to stop, all of that. And that is what machine learning can do for us. So instead of writing algorithm ourselves, where we have if-else statements, while loops, we would teach an algorithm to find patterns in a given sample data, and to then predict output for similar input data. Sounds easy, but let's address the elephant in the room. What is happening inside this magic prediction black box? One thing is very important. There is no magic in machine learning. There is no magic in artificial intelligence. Everything comes down to math, numbers, and artificial neural networks. Let's take one example. We have a canvas 16 by 16 pixels, and we have a hand-drawn number on that canvas. And we want to know what number is written on that canvas. First thing we need to know is that artificial neural networks They don't work with images, they don't work with text. They need numerical input, and they provide numerical output back. So we need to convert our image into a numerical representation. So now we have 256 numbers that represent our hand-drawn 2. That's an input that we can then feed into an artificial neural network. And bear in mind, that is a very, 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 very simplified form of an artificial neural network. But what you can see on the left-hand side, we do have those 256 numbers, which is our input values. And on the right-hand side, we have an output layer. So we have all the possibilities. So it could be a 1, a 0, a 2, whatever. In between those, we have hidden layers, layers of so-called neurons. The way those neurons work is that each neuron has a value, and that value is the sum of all the neurons from the previous layer times their weight. And the weight, that's the output of the training process. So when we have a fully trained neural network, it is able to predict that it is now 98% sure it's a 2, and only 0.5% sure it's an 8. And one thing we can see here as well is that on this first layer already, we have 1,280 initial connections, initial calculations to do. So there's just a lot of math involved into machine learning. Now, how can we use it on the web? There is a project called TensorFlow. It is an open source machine learning framework developed by Google in 2015. It was originally written in Python, but since 2019 it's also available in JavaScript, so we can use it in Node.js or in the browser. And one very important thing about TensorFlow is that those calculations, they are outsourced into so-called TensorFlow backends. That means we have, for example, a CPU backend where all those calculations are happening in JavaScript, which is quite slow. There's also a WebAssembly backend, where those are happening in WebAssembly. But if we want to have performant machine learning operations, we need to have access to the GPU. And there are two ways. We can use WebGL, because WebGL is this graphical abstraction layer that uses the GPU under the hood. It works, but abstraction layers are never a positive thing if you're talking about performance. So since Chrome 1.13, which was released around a year ago, and also in Chrome 1.21 on Android, which was released just weeks ago, we also have access to the WebGPU API. And the WebGPU API allows a direct access to all those modern GPU APIs like the Metal, the Vulkan, DX12, and so on and so forth. And it always depends on the operating system and also on the model, but it's almost twice as fast as WebGL. And there's also the TensorFlow WebGPU backend. So let's have a look at some code. I'm using here a very simple example of a face landmark detection model. All the slides will be online after the talk, so you will have all the links, you will have all the code there as well. I will just go quite quickly through the code examples. What you can see here is that we can import the face landmark detection model. We can then create a detector, and we can have this estimate faces method that basically accepts any image. Could be a canvas element, could be an image data object, could be anything, and it will then estimate the faces. And from those faces, it will also estimate the key points. And what I'm doing here is I have my canvas that is over my face, and I will just draw the key points on that canvas. I also have a more interactive demo. So let's open that. So what I'm doing here is I take the camera input. So I take the current frame of the camera. I will then predict the key points, and I will draw the key points onto the canvas, and then will take the next frame. So you see there's quite a lag between what's drawn on the canvas and my camera input. And that's because I'm using the CPU backend. I can now switch the backend to WebGL, and now it went from 5 frames per second to 13 frames per second. And if you now switch to the WebGPU backend, we are at 30 frames per second. So it's almost instant that it recognizes all the key points in my face. I released this little demo application on May the 4th last year. So for those of you who know, it's International Star Wars Day. So my idea was to add some Star Wars masks, where I have some key points between my eyes to determine the size and the position of the mask. And I can draw the mask just as a 2D image on top of my face. I also found a pretty cool example. I didn't build it myself. That maps the key points of my face with the key points of an example image. So that also means I can take this random guy from the internet in here, and it will now map the key points of the input to that image. And that's happening real time, directly in the browser. And I think that's pretty remarkable. I also built a Chrome extension, because Chrome extension basically they have run with JavaScript, CSS, and HTML. So we are also able to use machine learning in Chrome extensions. And my idea was to have this one Chrome extension where I could use hand gestures to navigate through any site. So let's take my own website. I can now start the Chrome extension. And what you see here is I have the cursor, which is between my fingers. Thank you, Tejas. And I can now use pinch gestures to scroll through the site. And I can also use it to click on certain links. And what it does under the hood is it will just take the video input, and it will take the distance between my fingers. And one thing you can see is that the center of the circle is not the center of my fingers, and that's intentionally because I realized that when I do the pinch gesture, I move my index finger way more than my thumb, so therefore I had to have this little offset there as well. Thanks. But let's get back to my initial problem, because I wanted to detect words when I'm speaking. And well, audio is not images, right? Except when they are. Because any audio sample can be converted into a spectrogram. And let's imagine I have 50 times me saying the word im Endeffekt. I could then create a model that I could then compare to 2-second clips of my talk. There is a TensorFlow model as well, a speech commands model. It uses the audio input. It will listen to the audio input and will look for those default words like 0, 1, 2, 3, 4, 5. And of course, my Swiss German words are not in that list. So I had to create my own model. And there's a tool called Teachable Machine, which makes that incredibly easy. Because what you see here is that on the top, I have a background noise class, which is just me talking for about an hour. Then I have 50 times me saying the word schlussendlich, and I have 70 times me saying the word im Endeffekt. I will then train that in the browser directly, and it will return to JSON files. I can now pass those JSON files to my speech commands create function. And since my slides are running in the browser, since the model is running in the browser, I'm also able to add that model directly to my slides. So let's open the recognizer. Let's start that. And now it's listening to what I'm saying. And whenever I say schlussendlich, schlussendlich, yes, it does work. So I did actually use this little tool in my second Swiss German talk, and it was quite fun because I did use the word from time to time, but at least I had a tool that told me not to overuse it. So pattern recognition is fun, but it's also pretty 2019. Nowadays, it's all about generative AI, natural language processing. So the question I asked myself is, can we run LLMs in the browser, large language models? Now, we do have WebGPU, we do have WebAssembly, we do have all those offline capabilities. So the real question should be, what does it take to run LLMs in the browser? Let's see how we usually use LLMs. That's basically, we have an instruction, We send this instruction to some magic function. Could be, or in most cases, it will be just a ChatGPT API, and it will return some text. Pretty basic. But if you want to run them on our device, we need to look a little bit deeper into what is happening in this white area. So first of all, I already told you that we can't use text with machine learning models, so we need to convert the text into a numeric representation, and we can do that using a tokenization process. So we will split up our words into tokens, and we can then convert those tokens into numbers, so we have numerical input. On the other end, we have the decoding process, where we then have a list of numbers. You can then convert those numbers into tokens. You can then concatenate those tokens into one big string, and we can return the string. Pretty simple. Now, let's look at the magic function inside of that. So if there's one thing you can take home from this talk, it is that there is no magic in artificial intelligence. It all comes down to math, numbers, and artificial neural networks. And of course, the artificial neural networks for an LLM is way more complex than the example I have here, but in the end, it's the same thing. We have a model architecture, which is the blueprint of how many layers, how many neurons per layer, how all those calculations happening, and we have the weights. And the weights, they are the thing that make our models as big as they are. Because if we take the Llama 2, for example, that's an open source LLM by Meta, and that's a 70 billion parameter model. That means we have 70 billion weights, 70 billion numbers that we somehow need to store. And if you store them in 16-bit floats, means you have 16 bits per number, 2 bytes per number, so we end up having roughly around 140 gigabytes. And that's just way too big to use in the browser. But there are also smaller models. There's, for example, the Gemma 2B, which is an LLM by Google, and that's a 2 billion parameter LLM. Those numbers, again, are stored in 32-bit floats, so we end up having 30 gigabytes. Still a lot. But there's a process called quantization. And with quantization, instead of using 32-bit floats, 16-bit floats, we will round them down to 4-bit floats. So we just have 4 bits per number, and that means we have for the Gemma 2 around 1.4 gigabytes in size. I get it, it is still a lot, but it is possible to use that in the browser. Also, those might be a little bit more less precise because, well, those numbers are rounded, but it's still precise enough to run, in that case, the Gemma 2B. On the other side, we have projects that try to bring those architectures to the web. There's, for example, Keras that is used by the TensorFlow.js and MediaPipe. There's Transformers.js, which is another web framework that we don't even have time to get into, but it's another amazing tool, and they are using the Onyx compiler and the Onyx runtime. And there is Apache TVM, which is an open source compile stack for machine learning models. There we go. And there is a Python tool called MLC-LLM, and that tool allows me to compile a model into a WebAssembly binary that then uses WebGPU under the hood to run all those calculations and takes the weights that it has stored in binary files. So for the tokenizer, we are at around 10 megabytes. For the architecture, we are around 2-point-some megabytes. And then for the weights, we are at 1.4 gigabytes. So we can round that all together to 1.4 gigabytes. Still a lot, but we can use it in the browser. So how can we do it? A couple of months ago, I created MDEdit. MDEdit is a markdown editor. And the goal originally was to have or to showcase some of those progressive web app functionalities like the file system access API, all those offline capabilities, file handling APIs. But then in the age of AI, I thought that I also had to add some on-device AI functionalities to this little application. So let's open that up. What you can see here is that we have this AI settings modal, and there you can download models. I have some tasks. So there's, for example, a translations task. There is a speech recognition task, and there's also text generation task. And what you can see here is that I'm using the Gemma 2B for text generation. That also means I can now open up a new Markdown file, and I can now ask the LLM to explain what is a GPU. So what is happening now is everything is happening on the device, so it will just token by token generate the response. Let's try it. And that's just incredibly fast. I have some stats here, so maybe it's too small for you to read, but to process the instruction, it can process those instructions at 138 tokens per second, and to generate the output tokens, so remember, we have each token goes through the whole large language model, it can process that in 32 tokens per second, so we have around 30 milliseconds per token. So that's way faster than I could even read. But we can also work with the text because we can just use it. We can then take the whole context and say explain this like I am 10. So it will process the whole context, and it will write everything like I am 10 years old. And again, it's just incredibly fast. I also added those other features. For example, we can translate everything, and here I'm using Transformers.js, so it's a model from Transformers.js to translate everything from German to French. And there we go. Everything happening on the device. And why is it still a Markdown editor? Because everything is written in Markdown, so you can also edit that stuff in Markdown, which was the original use case. So one question remains. AI in the browser. Are we there yet? Yes, we are. But there's always the small text. Don't know if you can read it. Maybe I could make it a little bit bigger. Well, I'm using the MacBook Pro here with an M3 chip, and the M3 is just the best chip that you can have for those kinds of tasks. I also have the same, or I also tried the same application with my Dell laptop, which has an i9 chip, which is also a pretty decent chip. But there I am down to around 3 tokens per second, so it's 10 times slower. It still works. I mean, 3 tokens per second, you can still write text with it, but it's crazy how big the difference is between the silicon chips and the Intel chips for now. And the problem here is that requiring specific hardware for your users is just not a very web thing that we want to have. But the future looks bright, because I think that there will be smaller and more efficient models with similar results. I mean, we came from a 70 billion token Llama 2 down to a 2 billion, sorry, parameters, not tokens, 2 billion parameter model with a Gemma 2B. Hardware will be more affordable. I think the MacBook Air, for example, they also have the M3 right now. So I do think that we will have quite decent results with the MacBook Air as well, and I also think that Intel will catch up quite fast. Also, on my phone, for example, I have a Pixel phone. There I have the Tensor chip, which is an AI-optimized chip, and right now I can't use that hardware with third-party applications or also with the browser. So maybe we will have access to those AI-optimized hardware as well in the future. And most importantly, we should use AI, or in my opinion, we should use AI as a progressive enhancement. I mean, now we are in this first wave of AI applications where everyone wants to create the AI image generation tool and the AI text generation tool. But for my Markdown editor app, MD Edit, I mean, it is a Markdown editor. It works as a Markdown editor on any device. But if you want to, you can opt in, download a model, use the model on your device. So it's a progressive enhancement. It's not required to use the AI functionalities to run the basics functionalities of the application. And there are a lot of upsides having AI in the browser. First of all, we can just send a link to our customers, send a link to our friends, and they are able to use our application. It's very interactive. So what you have seen with the video processing, there we are at 30 frames per second, and there's just no way to have 30 frames per second when we need to trigger some backend. Data stays on the client, so it's privacy preserving by default, and it also scales indefinitely. So even if every one of you now tries MD Edit, I won't have a huge ChatGPT or OpenAI bill, because everyone brings their own processing power. It just scales with the users that are using the application. So with that, I think AI opens up a whole new world for us to develop applications. And with the tools I showed you today, you are able to use them directly in the browser. So thank you very much for your attention. My slides are behind that QR code, so you will have all the links and all the repositories there as well. If you have any questions, there's a Discord channel. I will be there for the rest of the conference as well, so you can ask me there as well. And I try to be as active as possible on both Twitter and Blue Sky, so feel free to contact me there. Yeah, thank you so much for your attention, and I wish you a nice rest of the evening.